Hello, this is Rafael Jabba, and this is my video for electrical engineering class at Gloucester High School. These are not one of my usual circuits, as they don't really need any coding for them to work. So what these are logic gates, and they're what your phone, computer, or whatever else that you're watching this on uses to process its information. So there's a few basic gates that can be combined together in a few different ways to make complex systems like the ones found in all those devices that I just mentioned, or even something as simple as a calculator that you'd used for schoolwork. These gates would be called the AND, OR, NAND, and NOR, as well as the NOT gates. Each of the gates take a value from two or more sources, which is either a 1 or 0, and that's what the computers, they usually don't take in a range of values. It's either they take in binary information, which is either a 1 or 0. Then they will output one value depending on what the original values were. So, for example, if the gate receives a 1, or if the AND gate receives a 1 and a 0, it'll output 0 because the inputs aren't the same. It'll only output a value of 1 if both inputs are 1. The opposite is true for the NAND gate, which always outputs 1 except for when both outputs are 1. The OR gate does as its name suggests and outputs a 1 when either of the inputs are 1. The NOR gate will be the opposite, just as the NAND gate is opposite because it has a NOT gate at the end, and will only output a high value or a 1 when both inputs are low or 0. The NOT gate, all it does is simply switches the value. So if it's a 1, it'll be a 0. If it's a 0, it'll be a 1. These series of inputs and outputs are known as truth tables. So that is the graphs you can see right now. Each logic gate should have one to show you how it should perform. The main way that logic gates work in electronics is by using transistors. They're basically just small electrical switches that use electricity to turn them on and off and lets electricity flow through them if it's on and doesn't let electricity pass if it's off. In modern electronics, these are so small that there are billions inside your phone in just a little square about an inch big. However, the ones that you normally use to build circuits, like the ones I'm about to show, are much bigger. The main way a transistor works is by having three separate prongs or connection points. The first one is the collector, which is the positive input for electricity, where the main source of power comes in. Next is the base, which is essentially what activates the switch and receives the signal. And last is the emitter, which is the output, or where the electricity exits out, the flow. Electricity, it can only go through if the base is powered. So if there's no power going to the base, even if there's power going to the collector, nothing will come out of the emitter, or at least a very small bit, depending on what kind of transistor you're using. So these transistors, for what I'll be showing, I'll be having a physical slide switch, so basically just on or off, but can connect them up to other forms of input that are 1 or 0, and connect them up with other logic gates to make complex systems. Like you could even make a basic calculator if you had enough transistors. But I'll be using just some resistors and LEDs just to make a quick visual representation of the 5 basic ones. First, we have the NOT gate or an inverter. You can see how the circuit only needs one switch for the input. The switch just receives the 5 volts and allows it to pass if it's pulled down, otherwise no electricity will flow. If the switch is on, the base of the transistor will receive 5 volts. This will cause the 5 volts to be able to flow through the blue resistor and then through the transistor and straight back into ground. The electricity doesn't flow into the LED because it chooses the path of least resistance, which is the transistor, because it doesn't have a resistor to restrict the flow of electricity. If the switch is off and the transistor is closed, the electricity will have nowhere to go and instead go to the LED. You can see this when I flick the switch to the off position. Instead of the LED being off, it turns on. The AND gate is slightly different as it needs 2 transistors as well as 2 switches. It works by connecting the output or the emitter of one of the transistors to the input or the collector of the next one, which you can see with the purple wire on the bottom connecting the two black pieces. Electricity, it'll only have a path to flow through to the LED if both of them are powered, so both of their bases are receiving a signal. If one is off, the electricity will have nowhere to go and its flow will be blocked, which won't let the LED turn on. You can see right now that the LED is on because both of the switches are flipped in the same direction, which allows the electricity to pass through the resistor, through the switch, and into the base of the transistor. And that's allowing it to reach the LED. The NAND gate is basically just an AND gate and a NOT gate combined together. Its truth table is the exact same as the ANDs, but inverted. So that means that the gate will be outputting a value of 1, except for when both switches are turned on. When both switches are on, it will send the signal to ground instead of to the LED, which turns it off. You can see here when both of the LEDs are to the off position, they are on, which wouldn't work normally with an AND. And now when they're in any other position other than both being on, it's on, and when I set them both to on, it's off. The OR gate is very simple. It just needs either of the switches to be turned on in order for the LED to light up. This is done by joining the collectors and the emitters of both of the transistors. You can see it in the red wires that are coming from the 5-volt rail and the blue wire that's connecting the ends of both of the transistors. Their power and their output are basically just combined. You can notice that the LED gets slightly brighter when both switches are on. This is because the outputs are combining, and so the power that the LED is receiving is also combining. And this circuit can also be done just the same without transistors, but it doesn't really work as well. The NOR gate is similar to the OR gate, but it's inverse because it has a NOT gate on the end. That also means that its truth table is inversed, so that it'll only output a 1 value when all of the inputs are 0. So that means both of the switches need to be off. As you can see right now, both of the switches are off and the LED is powered on. Any other combination of the switches will turn the LED off. Circuit itself is pretty much the same as an OR gate, but the LED is placed up top